All right. I will not always teach you how to do these secondary problems. Okay? I've taught a new concept, and in math, what do? You learn a new concept, and then it's your job to incorporate it with all the other math you know. That's hard, but it's something you gotta. I can't. There's no way to do all possible ways you could integrate this one new concept with all old concepts. Okay, so I won't always be able to do this in class. Okay? Let's look at this question right here. We've got the function y equals x to the fourth minus 10x squared plus 9. We're asked to find the points on the curve that have horizontal tangent lines. Okay. If the curve has a horizontal tangent line at a point, what's its derivative? 0. So another way of asking this question, and I won't ask it this way, you have to make the leap, is where is y prime equal to 0? That's another way of asking this question. This is a much more straightforward way of asking the question, right? But I won't ask it that way. I'm expecting you to make a leap, a connection between a horizontal tangent line and a derivative being 0. All right, here we go. If I want to know where the derivative is 0, what should I go do? Let's find the derivative. Okay, what's the derivative of this function?
4x to the third.
Good?
Minus 20x.
Minus 20x plus 0, right? Okay. How are we doing, folks? Okay. Now, what if I said, find the points on the curve that have tangent lines of slope 28? What would I do? I would set the derivative equal to 28. I don't usually ask that question because we're not usually interested in where the slope is 28. But we might be, right? We might want to know if this was a position function, when are you traveling exactly 28 miles per hour? You would set the derivative equal to 28, right? But in this case, we want to know not where the derivative is 28, we want to know where the derivative is 0, because that's where we have what? Horizontal tangent lines, right? Okay. So here we go. We get 4x cubed minus 20x equals 0. Okay? Folks, I don't try to make too hard of equations for you to solve algebraically, but you do need some algebraic skills, including factoring. Especially factoring. Okay? So let's see here. I could certainly pull out a 4 out of both terms, but I could do one better, right? I could pull out a 4x from both terms. That leaves me with x squared minus 5. Okay? By the zero product property, if I have two expressions multiplied together to give me 0, then either the first one equals 0 or the second factor equals 0. So that tells me that either x equals 0 or x is equal to plus or minus the square root of 5. Folks, I need a hand. What is this square root of 5 approximately? That's approximately 2.3, 2.23. Square root of 5 is approximately 2.23. Great. Okay, great. That's all I need. All right. Now, did we answer our question? No, what did we find? We found the x-coordinates of where we had horizontal tangent lines. Now we need to find the y-coordinates. Okay? Folks, am I going to find y prime of, am I going to plug in y prime of the square root of 5? Am I going to plug the square root of 5 into y prime? If I do, what will I get? No, but we do it even faster. What will I get? I'll get 0. So don't find that. We already know what happens if you plug in the square root of 5 into the derivative, because that's where we found the value from to begin with, by setting it equal to 0. Instead, what do we want to find? We want to find y of the square root of 5, right? That's equal to the square root of 5 to the 4th power minus 10 times the square root of 5 squared plus 9. And if you clean that up, let's see there, that's 25. That's 5 minus 50 plus 9. Should get negative 16, I think. Okay. Similarly, if we find y of minus the square root of 5, we're also going to get minus 16 by the symmetry of that function. And what is y of 0? Y of 0. Oops, no, it's not 0. What is it? Thank you. Okay. So what are the points where we have horizontal tangent lines? They are the order pairs the square root of 5 comma minus 16 minus the square root of 5 comma minus 16 and 0 comma 9. Folks, we did all of this work algebraically, using calculus as a tool. Never once did we actually have to look at the graph of this function. This is extremely powerful. Okay. Now, I did provide you with the graph of the function and its derivative, big enough that you can make some notes on it. Okay. Blue is our function f of x, and red is its derivative. Does that make sense? Yeah, because blue was a quartic. So it's an even degreed polynomial, right? And red was a cubic, and you can see that. I think I need to zoom out. Well, no, we can see enough of that. Okay. I want to spend a little bit of time talking about this graph. Okay? I'm doing the hard work right now because I'm up here asking myself the right questions. I'm asking you guys the questions, but I know what questions to ask. That's actually the hardest job. Okay? Not answering them. I try to ask leading questions here. You want to practice asking yourself the same questions at home. Okay. Where is the blue function decreasing? Notice it. The first interval where the blue function is decreasing is from here to here, right? That's where the blue function is going downhill. What do we notice about the red function? It's precisely where the red function is negative. Where is the blue function going uphill? Between here and here. The blue function is increasing. That's precisely where the red function is positive. Okay? Now careful, folks. I am not asking the question, is the red function going uphill or downhill? I'm asking, is the derivative positive or negative? Not, is the derivative increasing or decreasing? That was a yawn. Okay, good. And notice that blue starts going downhill again between here and here. That's where blue is decreasing. And we see that's precisely where red is negative. Points that we're interested in this class, and we'll start to see applications in later sections. Okay? We'll start to see applications in later sections. But points that we're interested in is where the function has horizontal tangent lines. Notice, let me just give you a hint. Notice where a function has horizontal tangent lines for a well-behaved function is where it has maximums and minimums. Specifically local maximums and minimums. It's where the high points and the valleys are for these well-behaved functions. Those are precisely where the derivative is 0. Okay? So let's label a couple of ordered pairs on here. This is the ordered pair what? This is the ordered pair, the square root of 5 comma 0, right? Why? Because when we set the derivative equal to 0, we found one of the zeros was the square root of 5. What is this ordered pair right here? It's the square root of 5 comma negative 16. It's the point where the function has a horizontal tangent line. you can plot the rest of the points.